Okay, so this video is about completing the square. We've seen this process, actually two separate processes, but they're both called completing the square in two very different situations, and this is very confusing. So let's make it very clear. Two different situations, two different goals. One situation is we have a quadratic equation. It's an equation to solve. So what we want to find solutions. X equals something and something else. In the second situation, it's an expression, or you can say a function, that we want to rewrite. We want to rewrite it in the vertex form. Something like this: coefficient, then perfect square, x minus h squared plus k. We can denote these letters any way we want, but this is our goal. So as you see, the goals are different. The settings are very different as well. What is crucial when we work with the equation, that we balance it, left side and the right side. In this case, what is important that we preserve this equation, that we are not changing it, we are not making it bigger or smaller. This is so important that I wrote it down. The key idea that you should keep in mind as you work on these problems. All right, so let's get to work. The first one. So we want to solve the quadratic equation. We must preserve this equal sign no matter what. So in order to do this, we keep the first two terms on the left side, and we we add 5 to both sides. So we just want this number separately. So on the left side it's gone, and the right side it's now plus 5. Equal sign is still between them. All right. As you see, I left some space here because that's where my perfect square trinomial will be completed. So I'm thinking, what do I need to add here in order to complete the square? I want it to be like this. So I know that the first term must be x. Something must be added to create a double product minus 6. If 6 is my double product, then this must be 3. It should be minus as well because we must preserve that sign. So let's check that. If we expand this perfect square trinomial, we are going to have x squared minus double product 3 times x times 2, good, plus 9. So that's what I want. Okay, this 9 came from my head, from my necessity. In order to preserve my balance, remember the key, I need to add it to the right side as well. So I added 9. So my balance, my equation, my equal sign is safe now. Okay, so I am combining this 5 and 4, and it's a 14. I'm almost done. Now I need to unsquare both sides, remembering that when we unsquare, it could be either positive or negative. Oops, square root. Finally, I add 3 to both sides, so I have 3 plus minus square root of 14. This is my answer. I need to know that completing the square is definitely not the best way of solving quadratic equations. At least, definitely, it's not a universal method. In this case, it was pretty simple because the original equation was simple, because the b coefficient was even, and numbers are just not big. If this is not even number, then instead of, let's say it was a 5, this would be 2.5, which would make everything much uglier. If in front of x you would have a coefficient, then before you go to all of this, you would have to divide by this coefficient the entire equation, because it really works easily when you have x in the front without any coefficient. So it's a limited kind of situation when you can use it nicely. So I would not recommend it if you have a choice. All right. So let's look at the second one. It's the same expression as you see, but now it's a function that we want to rewrite. So I'm going to write it down again. X squared minus 6x minus 5 equals. So once again, this equal sign is important, but in a different way. in the first example, we had to balance our equation. So this equal sign, the rule of this equal sign was to ensure that the left side and the right side are always equal. Here it's different. What is unchanged now is my expression. I cannot change it because this is my given function. I don't want to increase or decrease it. I must keep this unchanged. So whatever I do to this expression, I need to make sure it doesn't change the value. All right, let's go. So I'm going to keep x squared minus 6x. And once again, I want to add something. I still have my minus 5. All right, so you already know that we need to add 9 and y. But can I just leave it like this? No, this 9 fell from the sky. I didn't have this 9. This equal sign would be ruined if I keep it like this. So what I do is I have to subtract this 9 to ensure that I didn't change the value of my expression. So what happens now is this is my perfect square, x minus 3 squared, just as before, and I have this leftover minus 14. So now my original expression and this expression, they're equivalent. They're the same value. Or I can just write my answer in the final vertex form. Just to mention, the point of it is to see the vertex of this parabola. So in general, HK would be the vertex. So 3 comma negative 14 would be the vertex. Or you can think about this as a transformation. Move 3 to the right and 14 down. And this is your 3 negative 14. And that's where your parabola originates. Just to look back at two problems again, really look back and forth, so it gets stuck. The different ideas, the different settings, the different goals, and the different concerns as you solve either this or the other type of a problem. And the key word that I would say that you need to remember, the key words, what are you dealing with? Either it's equation, where you balance left and right side, or it's an expression that you must preserve. That's it. Okay, let's look at a harder case. I need to tell you that to survive even like successfully, you may not ever need to do this. These are unpleasant, these are complicated. There is a chance you may see them, but if the previous part is hard, then you don't need to worry about this one. But I still want you to watch the entire thing because the idea itself of difference between these two procedures can be very explicit here. All right, so let's look. As I said before, we really don't want this 2 in the front. We need to get rid of it. And in the equation, we can do that. We can divide both sides of the equation by 2. We're allowed to do this because the equation remains balanced. So it becomes x squared minus 5x plus 8.5 equals 0. So much easier, except we have a decimal now. Oh well. So the process is the same. First, I want to get rid of this 8.5. And now I have x squared minus 5x plus, I still leave space for my to complete the perfect square, equals negative 8.5. Instead, I could have subtracted 17 from both sides in the beginning, and then divide by 2 anyway. So I would get this negative 8.5. Now, what will complete the square? 5 is the double product of 2.5. So I actually like to start with this before I even fill in this spot. I know that I will have x in the front, and this must be 2.5. Why am I always being negative? Let me change this problem. I'll make everything positive here. So it will be a plus now. So once again, 5 is a double product. So it must be 2.5 that will be doubled to give us a 5. Now, if it's truly a perfect square, when I expand it, I'm going to get square of the first, double product, which is 5x, and square of the second. So this will be 2.5 squared, which is 6.25. Now, I added this 6.25 just because I want to. So I must add it to the other side of the equation in order to balance it. Okay, I'm done now, almost. So on the left side, we already have completed square, and the 625, sorry. On the right side, it will be negative 225. Oh, actually, I am done, because I cannot take a square root of it. The solutions of this equation will be imaginary, and we are going to learn this later. But at least we know they're not real. No real roots. We can stop now. If you start taking square root of it, the calculator will tell you imaginary numbers or no real solutions. Okay. Okay, now we need to rewrite this expression in the vertex form. I cannot divide by 2. Why not? I cannot change the value of my expression. If I divide everything by 2, my function will be twice smaller. I don't want this. But I don't want the 2. With the 2, it's really hard to complete the square. So what I'm going to do, I'm going to factor out this 2. I will factor it out from the first term and the second term. Actually, don't need to break this 17. I can, but I will just keep it as is. It really doesn't matter how you do it. You just need to be careful anyway to preserve the value. Okay, so I should have left more space here. So x squared plus 5x plus what will give us perfect square? I know now it will be 625. But I just added it from nowhere, so I must subtract it now. Minus 625. I still have my 17. Oh, I actually made a mistake. Did you notice it? Pause for a second and think. Okay. So the mistake I made is what really makes this procedure pretty hard. So when I added this 625, I added it inside the parentheses. So in fact, I added double that. But I subtracted only 625. So I need to subtract as much as I added, which is 2 times 625, which is 12.5. All right. And 17 was never inside the parentheses. So it's just a 17. Okay. So now I have 2 perfect square. It will be x plus 2.5, just like before, squared. And I need to combine these two guys, so it will be 4.5. This is my vertex form of the expression, which tells me that the vertex is negative 2.5, positive 4.5. And the graph will be shifted 2.5 to the left and 4.5 up. For comparison, let me quickly write how it would look if I decided to factor out 2 from the entire expression. Maybe it's easier. So we factor out 2 from the entire trinomial, 5x plus 8.5, all inside the parentheses. So 2 inside. So we're working inside the parentheses, x squared plus 5x plus whatever I decide to add. I still have 8.5, and I need to add, I need to subtract what I added before, which is, as you know, 625, minus 625. So then inside the parentheses, I have x plus 2.5 squared, which is my trinomial, and a little extra, which is 225 again. But this 225 is inside the parentheses. So if I want to write it in vertex form, I need to distribute this 2. I multiply 2 over this square part and over 225, which becomes 4.5. So neither method is very pleasant. See whichever makes more sense to you. Okay, happy solving.